Okay, so last time we were talking about arrays and pointers and what happens when we use one array syntax to return and return that array, who owns the memory of an array, that kind of stuff, right? And we saw that out of our two syntaxes, we have kind of these two different guys for creating arrays. Now I'm going to create a little bit more separation here. This guy right here is how you create an array type in C++. Okay, this is the syntax for making an array. Now, as we looked at in the slides, how are arrays actually represented? Arrays are actually represented using contiguous memory. That is memory that sits right next to each other. All right, so when I say AR5 like this, it's going to give me a structure that looks kind of like this guy, where the memory addresses are right next to each other. And it's index 0 through, in this case, 4, just like strings would be. And the value of AR will be the base address. It'll be the address of bucket 0, which also is the base address of the entire array. Okay. But the type of that pointer, this kind of comes down to what we were talking about near the end of class last time, along the lines of in this syntax, why did we have to specify what kind of pointer we wanted this guy to be? Because I said memory is memory, right? Good. It would be a void pointer. What's a void pointer? Okay, well, so we'll start off with the statement that memory is memory, right? So when is the difference between an int pointer and a char pointer and a void pointer? When does that actually make a difference? It makes a difference when we do something called pointer arithmetic. Now, we're actually not going to spend tons of time on pointer arithmetic in here because that's something that's not real common anymore. You know, it's one thing to use an older language to show us some interesting stuff with memory and how things actually work under the hood. And it's a different thing of saying, here's this skill set that, kind of like rubbing sticks together to start a fire. Yeah, you still see that on Survivor shows, but usually you just bring matches or a lighter. Yeah. So in today's world, pointer arithmetic isn't necessarily a very common thing, but it does allow us to kind of at least talk about this generically. So if I have a void pointer and I add 1, so a void pointer is a memory address, right? Pointers, whenever you hear the word pointer, we're talking about a primitive type variable capable of holding a memory address. That's what a pointer is, right? Okay, so if I have this memory address and I add 1 to it, I'm adding 1 what to that memory address? Okay. Am I adding 1 int pointer, 1 size of int memory address? Am I adding 1 size of a char memory address? Am I adding 1 size of a memory address to that memory address? Okay. So when we start doing math with pointers, which would only happen if we're manually trying to walk through memory. Okay, which we can academically do, and we'll look at it in a minute. But it's not necessarily something we actually do very often. Okay, but if we did, if you take some value and you add 1 to it, you get another value. The question is you're adding 1 what? All right, if we take this into real world, if I have a bucket of apples and I add 1 apple to it, I have 1 more apple. But if I have a bucket of apples and I add an orange to it, now I have the same bucket of apples, but I have an orange in that bucket of apples. Okay, so just when I say add 1, it's add 1 what? This dictates what that would be. So if I say AR plus 1 here, I'm adding 1 size of an int pointer to it. That's the size step I'm taking through memory. If this was a void pointer and I add 1, I'm adding the entire address space to it for what was requested, because it doesn't have a It doesn't have a defined size. A void pointer is the size of the entire chunk that was created. So this doesn't really come into play for us in terms of actually using pointer arithmetic, but it does dictate why we said this is an int pointer, so that if I wanted to, for example, let's see, I fill it down here, don't I? So if I say AR at bucket 2, for example, that should give me a 2, correct? If I want to see here, I want to see different values in there. So now it should give me a 5. So I went and filled up my array with whatever I is plus 3. So bucket 0 would have a 3 in it, bucket 1 would have 4 in it, so on and so forth. Okay. So I can output that value like that, or I can say cout, give me the value of AR plus 2. Actually, here, I'm just going to say it like that. This is compatible with what I was about to, what I'm saying. If I say cout AR plus 2 like that, and I say, give me the value that lives there, we see we still get the 5. This relies on that idea of contiguous memory. This relies on the idea that all those values live right next to each other. So currently I have, this is a 0, this is a 3, this is a 4, I'm sorry. Yeah, this is a 5. This is a 6. That's not right, is it? This is a 4. This is a 5. This is a 6. This is a 7, because I'm adding 3 to it. All right, so 0. That's not right. 3, 4, 5, 6, 7. 0 plus 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. 3 plus 3 is 6. 4 plus 3 is 7. That's the current contents of our array. Even though it was supposed to be easy math, it wasn't. It didn't turn out to be easy math for me, apparently. All right, so this is the contents of my array right now. So if I say, give me what's in bucket 2, just using normal plain Jane array syntax, which looks very friendly, no big deal, says, go to bucket 2, show me what's there. It's a 5. This other syntax here says, go to the base address, which is 100, add to it 2. 2 what? 2 of the same kind of address as that guy is, which is an int pointer. So I'm going to take 2 integer size steps. That is 4 byte steps, 32-bit steps. So here's 1 step, here's 2 steps. Then I'm saying, give me the value that you found there. We put the asterisk there. It says, show me the value that you found in that place. And that's the 5. Make sense? Now, if you want to view contiguous memory, we can do something like cout AR, cout AR plus 1. Plus 2, plus 3, plus 4. And even though they're going to be scary looking memory addresses, notice they are exactly 4 bytes away from each other. 8 plus 4 is 12, which is a C. Makes sense? Okay, so these look a lot scarier than my 100 to 104 to 108 to 112 to 116. But it's doing the exact same thing. So we're proving that point that this is contiguous memory. Bucket 1 is 4 bytes from bucket 0. Bucket 2 is 8 bytes from bucket 0, and so on and so forth. Okay. But adding 1, 2, 3 to this guy is adding 1 size of int, adding 2 size of int, adding 3, size of int, because I've dictated that this guy is going to be holding a collection of integers, because I've asked for malloc to give me an int pointer, which means from this point forward, when I work with it, I do any sort of pointer arithmetic with it, it's going to take integer size steps through memory. But
So if you specify it to be a char pointer instead, could you still?
yeah, but you just mean you. So question is it gonna, no, I think we'll be okay. Well, actually, it won't make a difference here because we are, no. It's going to give us a very strange output. The answer is yes, we can. I made this guy a char pointer. Actually, this is going to be extra weird because what I said here is malloc says, give me some memory. That's what malloc says, right? Allocate memory. That's what malloc means. Okay, memory allocate. How much memory do you want? I want 5 times however big an integer is. Now we know an integer is 4 bytes, right? That's the size of an int. 32 bits, 4 bytes, 32 divided by 8 is 4. Okay, so that's how big an int is. So I'm asking for 20 total bytes of memory. All right. But then I'm saying, okay, but go ahead and give that to me as a char pointer. How many chars can I hold in 20 bytes of memory? A char, how big is a char in C++? 8 bits. You move up to Java, C#, it's 16 bits because it uses Unicode instead of ASCII. But bottom line for us, chars are different sizes than ints. All right. So I'm saying, hey, this is the number of bytes that I want. Just because I have the word int here doesn't mean this really has anything to do with ints. I'm just using the size of an integer as part of my math. So I'm saying, give me 20 bytes and label that 20 bytes as being of type char pointer. So now when I print out AR plus 1, plus 2, plus 3, plus 4, we're going to see they're only 1 away from each other. Question is it going to scream at me here? I might have to cast that to a char. Let's see what's, yeah, it doesn't like me to do that. So we'll just gonna do. Oh, problem is my type here. So I actually don't think we needed to do this. Yeah, if I wanted to return a char pointer, I better put it in something that knows how to hold a char pointer. All right, then we do need to do our cast here. Don't put ints in something built for holding a char. Oh, this is my yeah. But where am I calling my function? Oh, this is create array. I was thinking we were sitting inside of main. It's because my prototype. You're breaking everything. Then inside main, where I actually catch it. You know what? Oh, actually, no, I do need that for my because ultimately I do need to call create array. Oh, that's awesome. Why did I get the beeps?
Oh, is it like almost like a boot?
I must have generated something that the terminal here interpreted as like an audio something. This terminal probably is a I'm guessing UTF-16, so a Unicode based terminal. You know, this kind of goes down to, you know, what are you doing with this guy? You know, I'm saying go ahead and where am I seeing the star here? I actually want to see real quick. Is that happening when I'm filling it? So it's like it's death cry. Well, that's what I'm wondering.
Well, the good news is you made a program that makes cool people.
So was it the 7? Okay. So that means I should get 5 bells here. Oh, wait, they oh, because it went through so fast. So I generated funky characters. But I am interested in what if I don't make this a char?
Alright.
But where are my memory addresses? I feel like there's something there. Let's what's the what's the lowercase a in ASCII?
It's 100. No, 100 and sorry, 97.
All right. Oh, because when we're using C out, it's automatically noticing that this is a char and it's printing out the char. But at the very least, we saw that this is I'm literally filling my entire array up with A's, right? Okay. But notice my output here. Bucket. Let me just take away those guys. All right. So even though every single bucket of my array is a 97, I'm getting some different number of A's out of here. And it's because when I filled this guy up with a 97 has a size. So I put it bucket 0 and 97. When I took a +1 to that, because really this guy has up to 20 buckets in it, right? Because I know I'm storing chars. So I asked for 20 bytes of type char. This guy can now hold 20 of those. What I really wanted to look at here is what's the memory address of those, but C out is saying, oh, I found a char there, so you must want to deal with chars. I wanted to look at the memory address there. Okay, but what you're seeing is you're seeing these guys stacked on top of each other. So you're seeing a whole bunch of them at once. We're filling up memory. I have 20 bytes of memory. I'm going through and I'm saying, actually, what I want to do to make this more towards the direction I want to go with it, I want to set the value at AR plus I equal to that. So what I want to, I'm answering your question of can you store chars in it? Obviously, the answer is yes, but what I want to show you is if I build something capable of holding integers, and then I store a bunch of 1 byte things in there, I can actually store the value of 4 chars inside the space of 1 int. But if I walk through it as a char, see, I could, what if I store integers in there? Well, what you'll get is you'll get quarter numbers. So when you read the int, or when you read the char, you'll be reading the first byte of the 4-byte int. You'll be reading the second byte of the 4-byte int, the third byte of the 4-byte int, fourth byte of the 4-byte int. So you'll be getting 4 chars for every 1 int you walk. And if you're taking char size steps, you're going to get, if I mean to hold numbers in there, but I'm walking through it with steps the size of chars, I'm not going to get the numbers I expect. I'm going to get whatever the bits that are there convert to in terms of a decimal, which are not going to be the number you put in there. It's going to be some subcomponent of that. If I have a binary number like so let's set 1, 2, 3, 4, 5, 6. How many do I have there? 7. So if I have that, and I have that, you put these guys together. Okay, so these are two char size things. So this is half of an int. Size of short is what we're looking at there. All right. But if I try to say and I'm storing this here, I'll just copy this and duplicate it. So we're dealing with an actual int. This is what an int looks like in memory. Okay, an int is 32 zeros and ones in memory. Now, for small numbers, you're going to have a whole bunch of zeros followed by, the couple of bits that require you to give you the value for that number. Like the number 1 as an integer is 31 zeros followed by 1. Actually, it'll be 30 zeros followed by 1, then encoded into something called 2's complement, but this will be close enough to what we're dealing with here. So this is what an int looks like. But if I fill this guy up with integers and then I read it as chars, that's the first char. Let's assume do I have 8 of them there? It's going to read only the first quarter of that char as the first quarter of that int as a char, which is meaningless because I put a number. I put the number 294 into this entire int. This is a much bigger number than that. This is a number that is, up in the high number since I have a 1 in the far left. This is the 2 to the 32nd place here, but 2 to the 31st place, let's say. So this is going to be a big value. So I meant to hold some giant integer, but I can read out of it, and I'm sure we could play with this for a while and ultimately get it to give us the value by doing the right casting and stuff like that to say, well, what magical char did I create Frankenstein style by storing a big number here and then only reading the first quarter of it? What's that char? Even though I didn't purposely put any sort of char in there. So this is just us manipulating memory. Go ahead. Regardless of what the integer is. Correct. Yeah, the biggest integer we can hold is 2.1 billion, because that's what'll fit in 32 bits of signed space. But yeah, the number 1 would have a whole bunch of zeros followed by a 1. The number 2.1 billion would have a bunch of 1s. Yeah, but yeah, it takes up the same footprint, which I think is what you're asking. Yeah, even if the number is stupid small, this goes back to when we talked about the Y2K bug in the first couple of weeks of class or something like that. Like, why do we have so many different ways of holding integers, bytes, shorts, ints, longs, where, like, realistically, if I want to be a good steward of memory here, I should probably create a byte data type if I want to hold the number 1. At least I'm wasting the minimum amount of space, right? The number 1 only takes a single bit to represent it, but my smallest ability here is my smallest box I can buy from Target is an 8-bit box. So at the very least, if I'm storing the number 1 inside of an 8-bit box compared to storing the number 1 inside of a 32-bit box, I'm wasting a whole lot less space. Make sense? Now, the reality is that as computer scientists, we want to understand this. But the real reality is in practice, this is something you're not going to run into in modern day. If you're doing some sort of embedded programming or something like that for like writing software for appliances, dishwashers, stuff like that, you would be working with a language that might afford you the ability to do that. But at the same time, I doubt you'd ever do that, because you're not solving, time travel with a dishwasher, right? But yeah, I mean, your question's a good one, because that's a true answer to any type. Doesn't matter how big the number is, if it fits in that type, it will take up the entire space, even if it's just a whole bunch of wasted space. And we can actually see that with bytes real quick. I don't know if I've shown this to you before, but it's kind of an interesting example. If I say while true, byte B is equal to 0. We'll say C out B. And then we'll say B plus, actually, we're gonna say B equals B plus 1, because plus plus might only be defined for integers, not bytes, but whatever. That's not what I'm trying to show here, so I'll just avoid that bug. So I'm gonna say do this forever. So this is never gonna end. And we're gonna keep adding 1 to my byte. So B is gonna be 0, then a 1, then a 2, then a 3, then a 4. What's the biggest value we can store inside of a byte? 8 bits can hold 256 unique values. And since it's signed, it's negative 128 to positive 127. In the next course, 325, and I might mention it at some point in 250, the reason why you get 1 extra 1 on the thing, it has to do with something called 2's complement. You're going to learn in 325 how do we store signed numbers, positive and negative numbers. We don't have both a positive and a negative 0. So you get an extra number on one of the sides, and the way the math works, you get an extra number on the negative. Because we don't need a plus, we don't need a positive 0 and a negative 0. All right, so the question is if I so the largest positive number I can store inside of a byte is 127. What happens if I add 1 to that? What do I get? Well, as a human, we say, well, 127 plus 1 is 128. But does 128 fit inside of a byte? No. You take, if you say 128 and you write it as a bunch of 0s and 1s, you now need more bits. You can't fit that inside of 8 bits. You need 9 bits to store 128 in a signed format because of this 2's complement thing. We only get to work with 7 of those bits is the punchline there. So what happens when I add 1 to something, effectively overflowing? Or what's the beginning for a byte? You're right. You're right. It will loop back. We're starting it at 0 here, but what's actually the smallest number we can store in a byte? Negative 128. Yep. So we're going to see this go 0, 1, 2, 127 to negative 128, negative 127, negative 126, all the way up to 127 to negative 128. So it's just going to be this infinite circle. Which library is the byte data type stored in? Here. Does it know about shorts? This will only make us go up to 32,000. There we go.
Might take a-
Oh, it just skipped. There we go.
Well, I mean, we're seeing it happen. Yeah, the whole reason this is slow, this is actually another interesting thing. I don't know if we've talked about. We're running into computer trivia type stuff here, but I mean, it's good. You know, this program seems to be running relatively slow, right? But we're seeing my looping point, right? As soon as it gets to the biggest number, we add 1, it loops all the way back to the smallest that can store in there. And this isn't like, oh, it says, well, if it's too big, go to the smallest. This is how binary math would work. If you add 1 to it, you've now, you have it's fallen off. So you have a bit shift, and now when you do 2's complement and undecode it, the new value after you've dropped that last 1. So a whole bunch of 1s plus 1 gives you a 0 over there. Now you're at the far negative extreme when you decode it. It's not doing some sort of if statement and saying, oh, well, this is bad, so reset it. This is how math will work with binary numbers. Go ahead.
You're not going to get an overflow.
Because I don't have an overflow error.
Yeah. Right.
But overflow is the right word. What you're saying. So effectively, when I add 1, I now have more than will fit in the bucket.
Yeah.
So what ends up happening is instead of getting you were expecting an error from having too much. No, I just lose a bit. The bit falls off. So now I have what's left after I added that bit, which happens to be the 2's complement version of the biggest negative number, the smallest negative number. You see what I'm saying? It's not an error. It's just this is the number you now represent. You have 8 bits, you add 1 to it, and now you have 9 bits. I can't hold 9 bits. That guy falls off the cliff. So now you have this new value that's left over after I try to do the math of adding one, and that happens to be the full negative number, again, in this thing called 2's complement. We encode negative numbers in something called 2's complement. All right, but we're watching this guy do his thing. Oh, he finally freaked out on us. Like, look, this is not what you want to be doing. Oh man, how much of the stuff am I going to lose when I reload? Can I save? Oh, it looks like I can. I didn't get all of it back, but I got enough of it back for that little, because we just had our little example thing there. That's fine. So the other thing I'll show right now, since we're at this thing, is if I have we'll just use an int here. So int I is equal to 0. For int I is equal to, well, I don't even need that guy. 0. I is less than, it's 200,000, 2 million, 20. Is that 2 billion? Must be. Oh, I don't do my I++ there. All right. So this is counting. It's not going to loop back because I'm only going up to 2 billion. 2 billion fits inside of an int. Oh, I guess it did. That's not 2 billion. That's 20 billion, I guess. Okay. But regardless, if I take that same program, all right, we let that guy, is it looping back on that? No, it's an int. That's 200,000. That's 2 million. Yeah, well, that should fit. Why are you doing this to us? I feel like it has to be something with online GDB not wanting to. Let's see when it runs out. I'm trying to look at the number when it goes negative. Oh, were we doing? Oh, do we still have our loop down here doing something funky in create array? Oh, we have our while true. We never got to see the thing I was trying to show you. We never got to see because I had my infinite loop down here. We were calling. All right, but in any case, now we're seeing this guy. So obviously, this program's taken a while to run, right? So now if I just do one thing here, I say int count is equal to 0. And inside here, I say count is equal to count plus 1. And then I say cout count at the end. We're going to see that this runs much more quickly. So the question is why? This is also a computer organization and an operating systems thing. This is a 325 mixed with 350 question. Go ahead.
It's time to display it and it'd be much faster to just do all calculations and display the result.
Display once.
Yeah.
And it's even worse than that. So you're right. IO, input output, is expensive. Writing to the screen is expensive. It takes a lot of time to display something to the screen. But it's even worse than that when you're dealing with scheduling and operating system scheduling for the processor in your computer, saying, okay, you work on this problem. So I mean, that's how our computers work. If anymore, we have 4, 8, 16 core processors and stuff. But let's roll back a little bit to when we had a single core processor. You literally can do one thing at a time. You know, how did the computer make us believe that more than one thing was happening? It, was really, really fast. So it said, we're going to do a little bit of this, then we're going to do a little bit of this, and we're going to do a little bit of this, then we'll go back and do a little more of this guy. But it's happening so quickly that from a human's perspective, it's all happening. It's all happening at the same time. Well, so and when you're in 350, you'll talk about scheduling algorithms, different ways we can tell the processor when it's time to pause one process and move to another one. That pausing thing is called a context switch. So when we tell one process to go ahead and pack all of its bags, remember where you left off, because we need to load another guy in here, and we'll give you go back at the end of the line, and then when you're ready again, we'll schedule you again. Writing something to the screen immediately interrupts the process. So that means, let's say, we'll keep it in human time. Let's say that each process gets 10 seconds on the CPU. They get far, far, far less than that. But let's say they get 10 seconds on the CPU. The very first thing that this guy would have done when it got on the CPU is try to print something out. So in the first microsecond of his 10 seconds, he says, I need to write something to the screen. And the processor says, that's not my department. So he immediately kicks him off the CPU for it to go do IO. So we spent all that time, that idea of a context switch, the whole unpacking your bags, packing, remembering where you left off, takes time. And effectively, we're saying you get on for a microsecond, say you want to print something, we kick you off, it goes and prints its thing, you get back in line, you get back in, unpack your bag, say, I want to print something, we kick you off, so you're going to pack your bags, get off, or it's going to go print, get back in line, slow. Where if we're just in there doing the math, maybe this happened in one pass through the CPU. Maybe it took 2 or 3 passes through the CPU, depending on how much time this process was getting on the CPU. But from our perspective, it happened quickly. And then we just did a single print to the screen. That guy was expensive, but we didn't notice it because we only did it once. We didn't do it 2 billion times. Make some sense? Okay, so another example where IO is a good way. When we write something to the screen, it's a good way for like debugging and stuff. But if you write stuff too often, especially inside of loops and things, you've just slowed your program way down in terms of the actual physical time it takes to run. Yeah.
So along with that printing out to the screen, is it converting from its binary to its decimal equivalent?
Well, yeah, because internally it's stored as binary, but that's not taking real time. In fact, it's not actually converting. The conversion would have happened at the time when it went to store it, because ultimately it's stored as binary. I guess since it's printing it out as a decimal, it's converting it back, but it doesn't take time, not measurable, not noticeable time. Okay, so concept there is programs that write a lot of stuff out to the screen inside of a loop run slower, because input output, writing stuff to the screen is expensive. That doesn't mean it's wrong. It just know that it comes with a cost of writing something out to the screen instead of just letting it focus on the math side of it. All right. So since we've been just talking about trivia crap here, really. And important stuff, and it's interesting stuff, and it is part of computing, but it's not really the practical programming stuff. Even the pointer arithmetic stuff, I'm sure we can sit here and massage it until we finally can convince this guy to show us quarter inch, whatever the first 8 bits of a 32-bit thing are as a char or something like that. I'm confident that we can eventually figure out how to get this guy to peel apart our ints like that, even if we have to move stuff into other data types and do something called bit shifts. We might even have to do that, just bit shifts, and say, hey, just show me the first 8, show me the second 8, show me the third 8, show me the fourth 8. These are all doable things, and we can prove the point, but it's not going to help us in here. All right, so, and I'm not going to test you over the stuff we've really talked about so far today, because this is really more of the foundation of kind of how arrays are built, and how pointers work, but not really applied programming. So it's not going to be something like on an exam where I'm going to give you some binary thing and say add 1 to this or something like that. It's not going to be like a trick question. Most of the stuff will just be programming stuff. So now let's look at something that is actually going to be practical for us. So we're gonna go ahead and create a couple of arrays again. So I'm gonna say int, call this guy AR1. It's gonna be size 5. And then we're gonna say int pointer AR2. And he's gonna be the int pointer version of calling malloc on 5 times size of an int. Both of these guys are going to be 20 bytes in size. Well, that's not the most accurate way of saying it. Both of these guys will ultimately request 20 bytes of memory from the operating system. Okay. So now let me just show something real quick. We're not going to actually go into this very much. I just want to show you, this will indicate the problem we have. How do I know, if you remember from last time, and also we've seen it here today, I went through it, I just hard coded. I knew we had 5 elements. So all my loops had like for int I equals 0, I is less than 5. You know, I just said, oh, we know it's 5. Let's focus on the array part of things. But how do I generically know how many elements are in that array? How could I get that 5 out of that array? Go ahead. You would wish. Yeah, you would wish you could. Newer languages, Java, C#, absolutely. They have dot length. Actually, it's a dot length field. They have instead of methods, but same thing. You can just ask the array, hey, how many buckets do you have? And the array will say, I have 5. No problem. Okay. Older languages like this can't do that because arrays are primitive types, not object types dressed up as a primitive. I think that's maybe the best way of putting it. Arrays in modern languages are stored more modernly. So they have some additional meta information about themselves that they can advertise. But in this particular case, arrays in older languages like C and C++ are primitives. They can only hold a value. Now, they do happen to behave a certain way. When I say go to bucket 2, it takes 2, in this case, integer size steps through memory, trusting that what was requested was done in contiguous memory, but it can't just say, I have 5 buckets. Make sense? All right. So now we might make a guess. We might say, okay, well, what about the size of thing? How does this guy work? You know, when I said size of int here, so if we do a cout size of int, what am I expecting the output of that to be? Well, no, what's the size of an integer? 4. Okay. Okay. And another equally decent guess might be 32, right? Those mean the same thing, but it happens to output in bytes. So this is going to give me a 4. The size of an integer is 4. If I say, what's the size of a char? It's going to give me a 1. Size of a short is going to give me a 2. 16 bits instead of 32 bits. So on and so forth. All right, makes sense? That's what size of does. What's the size of AR1? So it wouldn't be unreasonable for us to say, oh, well, maybe I just use size of, and maybe he'll tell me how many elements are in there. It's not an unreasonable consideration, right? All right, so what do we get? We get a 20. What's 20? Okay, so 20 is the total number of bytes stored in AR1. It's like, oh, well, you know, maybe I'm on to something here. Maybe so can't I do this? Can't I say then size of AR? Oops, sorry. Divided by size of int and get me my 5 that way? Ah, perfect. We figured it out. Almost. Right? We thought that was a decent idea until we go and say, well, what is, let's just use our one line so we don't confuse what's going on. What if I say, what is the size of AR2? Remember, the size of AR1 was 20, right? And we've advertised that AR1 and AR2, these guys are effectively the same thing. It just comes down to who owns the memory, right? As it's written right now, they behave the same way. because they were both defined inside of main and there's nowhere to go from here. So these guys will remain in memory until main dies. All right, that's what we looked at last class. So if the size of AR1 was 20, we would make the assumption that the size of AR2 is also 20, but it's not. The size of AR2 is 8. So rut-row, okay, that's a problem. So now all of a sudden we can't just say size of AR2 divided by size of int no longer gives us our nice clean, there's 5 elements in here, right? So then maybe you say, okay, well, then we should just always do it this way. Well, until we do something like void, let's say print size, and this guy takes an int pointer as a parameter. And we see out size of AR. Like that. So that's all that guy's doing. It's just printing out the size of the int pointer that was passed in. So now I can say, well, we saw that see out size of AR1. We saw that was a 20. Print size AR1. Rut-row again. Like, okay, well, it behaved the way we wanted it to behave for a moment until I started tossing it around as an int pointer rather than allowing it to live inside of this kind of pretty array type structure that's built for us. So we really can't rely on that throughout our program to get the size of a int array. The only way we could pull it off is have a function that specifically is expecting an int array of size 5. Then we're not requesting generically how big it is, right? We pass things around by memory address, and that's fine. We like to rely on the fact that, hey, I know that arrays are stored in contiguous memory, so I can just pass around where this guy begins, and now I have access to all the things in the array. That's not a bad concept, right? It's the requirement. The trade-off is you need to get a size of land right next to each other in order to store your arrays, in order for arrays to work. You know, because they rely on bucket 0 being here, bucket 1 being 1 step from that, 2 steps from that, 3 steps from that, so on. But as soon as I need to hand it off to another function, I'm passing it by an int pointer, and pointers are variables capable of holding addresses. It doesn't know that that's an array or just the address of just a single int, right? I can pass to that same print size. I can say we have int a is equal to 5. And I can pass this guy the address of a. That's an int pointer, right? A is a int. The address of a is a pointer to an int. We still get our 8. So from that function's perspective, an int array, something that we know is an array, has the same size as something that we know is just a single int, because that's how big a memory address is, right? So it's not telling us how big the value inside this is. It's not telling us how big the value that lives inside of this guy is, all those integers added together. It's saying, you asked me for a memory address, great. Here's how big memory addresses are on this computer. They're 64 bits. Make sense? 8 bytes. All right, so that kind of throws it out the window of being able to use that little magic trick to get the size of an array consistently. Go ahead.
I was gonna ask first value? With the total size?
Well, you can sort of pull that off as long as you're in the right environment, just like we can do this here. You can, if you pass the two addresses, the address of the last bucket and the address of the first bucket, you could just subtract and get the total number of bytes, the difference between those two addresses, right? That's pointer math at that point. So if I have address 120 and I subtract from an address 100, I'm left with 20. Okay, but then you're still having to give it two pieces of information. What's another thing we could do? Well, we can kind of, and this is how strings work, old style strings in C, and even the new style, I promise you, under the hood works this way. What it does is it has a string termination character. \0 is the special hidden character that terminates a string. So you can pass an old style string to a function and start walking it from bucket 0 and say, I'm just going to count until I finally hit a \0. When I hit a \0, I'm at the end of the string. Therefore, that I have the length of the string. It's the number of things I counted, right? So we could sort of fake that in an array, right? We can just put in the very last bucket something. But if I have an integer array, what do you put in the last bucket? Maybe you say, well, I'm just going to put a -1 there. That lets me know it's the last bucket. Well, what if you also wanted to store a -1 somewhere in the middle? A legitimate -1, not a end of array -1. So again, it's kind of a hack, right? So knowing what you know right now, what's the cleanest way of being able to pass an array to a function and maintain and know what's the size of that array? If I want to write this function print size and have it take in a pointer to an array and print out however many elements are in that array, rather than like I have right now, I'm assuming this guy is 5. How can I make it so that I don't have to assume that this guy only prints out arrays of length 5? He instead will print out arrays of whatever size they are. Knowing what we know right now, just using the toolbox that's in front of you, how can we solve this problem? Go ahead.
Would you like pass it to the array? Would that work?
Can't really, the way we pass in an array is with a memory address. But go ahead, then I'll give you a hint.
And the only way I think would be every time you add something to the array, you have a separate variable to keep track of that you've added something and you're adding something to the array.
Okay, well, how do you access that variable inside here? Oh, so just pass 2 values, right? Here's my array and here's how big it is. We've seen it before. Let's roll back in time a little bit and remind ourselves what main has looked like at some point. Actually, I'll write it as I'll write it as main. Old school main takes in 2 parameters. Remember, these are for command line arguments. How many command line arguments are there? And what are they? These are strings. This is an array of strings. This is also sometimes written as that. So this is an array of char pointers, which are strings. And this is how many of them there are. Passed in 2 pieces of information. Here's my array, so you know where to start, and here's how many things are in there. Not rocket science, right? You can't ask the one guy how many things are in it, so I'm just going to give you both pieces of information. No problem. Now, you're probably going to have a value somewhere that allows you to generically remember that. So maybe we have something like if we go and we say we're going to change print size, but we're going to print in pass the array, plus we're going to pass in the size, take in 2 values. And then for print array, this guy will also take in the size. So now we can say print out size. And then in here, we're going to say 20 here. And we're going to say size of array there. Now, when we call print array, we will pass it our array, AR2, and we'll pass it the size. We'll just give it those two pieces of information. And right now, we didn't fill it with anything. So since it's an integer, it's going to print out a bunch of zeros because that's the default value for integers, which we hate, but it's a thing. But we could write a little loop here for int I is equal to 0. I is less than size of array. I plus plus AR2 at bucket I is equal to I. That'll fill it up with 0 through 19. Too many arguments to print array function. I call it someplace else then. Where do I call it? Oh, I didn't change it in my print array here. I added it to the wrong function. So there's my 0 to 19 from my print array. And if I change this guy to 30, it will be 0 to 29. Because now when I call print array, I'm passing it the pointer to the beginning of the array and how many things you're going to find there. Now, another solution to this that was somewhat common in, let's call it older programming, and I'm going to kind of give you a misnomer. You could just create a global variable. So I can create a variable up here. Int size of array is equal to 20. I can dump that guy there. And if I have that guy global, see, notice he is outside of main. So since he's outside of main, I have access to him throughout this entire program, which means I no longer need to pass in two pieces of information here. I will need to call this guy size of array, because that's the name of my global variable. So if I'm inside a print array here and I say, here's a variable called size of array, what's the scope of size of array? I immediately look locally. Do I see any variable defined here called size of array? Really, I'd be looking at something that comes before I start using it. Is anything in there called size of array? So I might immediately be suspicious that, okay, this is going to be an error. But if I scroll up and I happen to notice that I have this global variable called size of array, this guy is accessible inside of main. He's accessible inside of all of these functions because he is outside of the scope of any individual thing. And instead he lives at the global scope inside this program. So we might say, oh, well, that helps us solve a lot of problems, right? And the answer is sometimes the answer is yes. One thing that you will hear at some point in your career will be global variables are bad. Never use global variables. I would say be careful before you use global variables. And the reason has little to do with global variables being bad. It has more to do with it's very easy, especially for beginning programmers, to abuse global variables, where whenever you run into an error in your program dealing with scope, you just say, oh, well, I'll just define it up here. Now he knows where to find it. So when your program's done, you have 40 variables at the very top of it that are used throughout your program all over the place. And you've just defined them at the very top. So you have every variable that you've used in any of your functions just globally available because that's what gave you the least number of errors. So if you use a global variable, use it with the knowledge that this is a good idea, not that it's the thing that made the error go away. I would also maybe extend that and make the argument that when is it okay to use a global variable? When you need to use that variable in more than one scope. You might even say more than two scopes, because maybe if you only need it in exactly two, you just pass it to it like we did in our function. We just pass the second parameter. Here's the array, here's the size, done. But if you do need to use a variable in 3, 4, 5, 10 scopes, maybe making it global is superior to passing this guy through the parameter list 20 times. Make sense? So there is a middle ground here. It's not a good idea or a bad idea. Okay. And you run into this even in modern things like with Android programming. When you launch when you hit a button on your in an app on Android and it launches another screen, that thing's called an activity. All right. And in Android, activities have a they kind of come with a little backpack called extras. Okay, so inside of this thing called an intent. Don't get too far in the weeds here, but effectively, when you launch an activity, the activity comes into existence holding onto a backpack called extras. So if I want that particular activity to have access to a bunch of variables, I can throw them into that backpack before I launch the activity. And then when the activity becomes alive, he drops his backpack, opens it up, he starts pulling variables out. He's got them, right? I was able to get data from one activity over to the other activity. Well, what if I have 10 different screens in my app that all want to know who the current logged in user is? Now you have 10 scopes that all need to know the same pieces of information. Well, sure, I can just throw that value into every single backpack that I ever send any of my activities out with, or I can toss it up in something. The global thing across multiple objects is something called the singleton. We'll talk about it probably next semester, but I could just throw it up in the cloud, the singleton. Say, hey, you guys want to get that information? Just ask the global scope. He's got it. It's the exact same argument we have here, though. If you only need to share it with one other screen, just put it inside the backpack. If you need to share it with 20 screens, maybe at that point it becomes pretty inconvenient to pack everybody's backpack with this piece of information when you could just throw it there once and everybody has it. Make sense? So global variables are not innately bad. They just can be easily abused. So it's the whole, great power comes great responsibility, yada, 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 eat your Wheaties. The last part was supposed to get a giggle. I got nothing. It's a tough crowd today. I hate all of you. You're all right. Today, just today. Actually, he's okay too. He asked a good question earlier. So two of you passed muster today. Oh, she had a good answer earlier. 3. The rest of you are dead to me. That's all recorded. They totally pulled out of context. My teacher said I'm dead to him. Immediately, I immediately get canceled. Yeah, at least I'll probably make an appearance on Kimmel or something. Wisconsin teachers get canceled after saying his students are dead to him. Tonight at 11. All right. So do we kind of see the point here of, if we realistically speaking, in our relatively small world right now where we're not calling 30 different functions, our programs are still pretty small, that the go-to move for us right now, if we have an array and we're going to pass it to another function and we want to be able to deal with that generically like we did with print array a few minutes ago, you just pass in 2 parameters instead of 1. Here's my array, here's how big it is. Sure, we got to keep track of 2 things, but that's what we have in our repertoire right now. Make sense? Okay, so now we're going to say that that's tolerable, right? We can live with that for now, but there must be a better way. Right now, I'll short circuit this a little bit for some of you who've had some of this stuff before. Yes, there are things built into C++ that allow you to carry the number of elements, or there's actually an array type in a more modern version of C++ called array that will allow you to give it the size and then ask it what the size is. You can use things called vectors that also carry the size. These actually, some of those things start falling into a category of things we talk about in CSC200, the third programming class, when we talk about data structures and something called linked lists, or linear and nonlinear linked data structures. They sound more complicated than they are, but we're going to say that we can't use those things right now because it doesn't take us on the right voyage up the mountain. You know, we're not just taking a helicopter up to the top of the mountain and say we're good, because we want to understand where we're going from here. And we also want to use this as an opportunity to introduce objects, right? Now, one thing we could do even before objects is, couldn't we create a struct that holds an int pointer and the size? And just call this guy, you know, array struct, int array struct, right? And then I only have to pass one parameter though. It just happens to be one parameter that has two things in it, right? So we have fixes for this. We just have to be creative with our tools. But we want to start rolling towards this idea of something called a class. All right. And inside of our classes, what we're going to do starting next class is we're going to create an array that is, we're going to create a class that allows us to instantiate an array with a certain size, and then we can pass instances of that class around and say, what is your size? Go through, loop through whatever number of things, similar to what we could do with a struct, but it gives us our kind of our gateway drug to introducing classes. Okay. But in the meantime, since we haven't had homework for a while, and he's such a big fan of homework, I've decided to pile up the last 7 assignments that we haven't had into one just hell weekend.
That's called the hackathon.
Is there a hackathon tomorrow? Is there really?
Saturday.
Saturday. Yeah.
How many of you are going to the hackathon? All right, you're getting this assignment. If we had a lot of hands up, I would probably not give you homework over the weekend. Stand by your dead to me comment. All right, homework. Write a program that creates a 100 element array and fills it with random integers. And you've done random integers before with our dice roll stuff. Your program should display the unsorted array of integers, and then it should sort them somehow, and then display the sorted array. Okay, I am not asking you to use some built-in function to sort, because we haven't introduced the built-in function to sort. I'm asking you, I would say in the ideal world, try to invent your own algorithm for putting a bunch of things in order. Just pretend like you are sitting there with 10 pieces of paper in front of you with different numbers on them, and you ask yourself, what would I do to get these guys in order? Right? You go through and you first find the smallest one, and you put it here, and then you go and find the next smallest one, and you put it here. Now, I promise you there are algorithms that are better than that. Okay, but I want you to come up with a way of putting a bunch of numbers in order. So fill an array with random integers, put them in order. Don't use a built-in function to do it. All right. If you want to go and learn how bubble sort or something like that works, you can, and then use that as an algorithm. But I would encourage you to try to come up with your own MacGyver solution to sort it, and you're probably going to end up being something close to one of the weaker sorting algorithms at the end. All right. Submit a link to the code and the self-assessment. And I don't know how much it'll be helpful, but I'll go ahead and give you my current code as a all right, questions, comments, concerns, bribes. All right. Go to the hackathon. Hackathons are really good experiences. If you're not doing anything on Saturday, or even if you are doing something less important on Saturday, go to the hackathon.
I was trying to write something that, like the death match we had.
Yep.
but 4 people. And a bunch of different